people coming in, but we got a lot to cover, so I want to make sure we have enough time to get to the fun stuff. So this is bringing reality into SOLIDWORKS, reverse engineering with 3D scans. Now this is something that's kind of a personal project of mine, something I enjoy doing. It's something up until a number of years ago, it's not really a topic that came up very often because 3D scanners are something that only people or large corporations could actually attain. But nowadays you can get 3D scanners for a couple $100. Most of the scans I've done we're done with a $300 scanner, so very inexpensive. And it's kind of brought up an interesting point that SOLIDWORKS was never really designed around a point cloud or a mesh geometry, so they had some kind of workarounds to make it better, but it's still not quite as intuitive, maybe not as user-friendly as it might have liked. So this is my process for working with those scans in SOLIDWORKS. Now, as you might have guessed by the shirt and the branded slides and everything else, my name is Austin Popejoy, and I work for Swift Solutions. We're a reseller here, headquartered in Michigan, but I'm actually in Wisconsin, and that'll be relevant a little bit later in the presentation. But we're going to go over a couple of quick topics today. We're going to start off with file preparation. Getting your files ready is just like painting a car. You have to do all the groundwork first, otherwise everything after that is going to be a horrible experience. So we're going to start off with file preparation. That's going to be the majority of this first section. And then we're going to go into reversing and engineering a part that's prismatic, so something you could probably do with calipers and measurements, but it's going to be a segue into our reverse engineering organic designs, which is something that's going to be a little bit more practical for what most of you are probably looking for. Now I do want to make a quick disclaimer. This is not about a particular scanner or any scanning process. We're going to assume at this point you have a scan ready to go. There's far too many things out there to actually touch on that and make it relevant. For the scans that are using this, I use the Creality Scan Lizard, which is an absolutely horrible name. I have no idea why they came with that. It has to be something lost in translation, but for a scanner for a couple $100, it's actually pretty good. The main one, I also had a prototype unit from a company called Riven. They are no longer around, unfortunately, but they had a phenomenal scanner. And also I have a Next Engine scanner that I use for some of this as well. But I want to point out this is not the only workflow for working with scans with SOLIDWORKS. This is what I do. It's not the only way to do it, and it very well may not be the best way to do it. I'm sure there's enough people in here that you can actually improve on what I've done as far as the groundwork goes. This is going to be all within SOLIDWORKS. We're not going to use any third-party add-ins. There are a ton of them out there for SOLIDWORKS. Scandia 3D is an add-in that you may have access to. There's also Geomagic, Polyga, and a whole bunch of other ones. If it makes financial sense to you to have one of those, that may be a better solution. But I know like Geomagic, I think last time I checked was like $28,000 for a license. That's not going to be really worthwhile for something I do as a hobby project. All right, so now get into the fun stuff and talk about file preparation and why this is relevant. As you guys know, SOLIDWORKS was not designed around mesh geometry. It doesn't handle it well. If you ever tried it, you probably had a bad experience and everything crashed, and that's why you're sitting here. The important thing is how many faces and facets your model has. Now, depending on your scanner settings, this could be a huge number, could be slightly less, but most of them are going to be more than SOLIDWORKS can reasonably handle. This basic model here, which is a little 6-inch part with a cheapy Creality scanner, put out about 300,000 faces. And if I tried to open that in SOLIDWORKS, it took a little bit over 8 minutes to open on my computer, which is not a powerhouse or anything, it's just a standard laptop. But it took 8 minutes. Now, with the workflow I'm going to show you, I took it down to 200,000, so a reduction of a third, and that dropped by 50% opening time, just over 4 minutes. Take that down another step to 100,000, and that dropped the opening time 85%. And the important thing is, I reverse engineered off of all 3 of those models, and they came out exactly the same. So you're not losing any accuracy, it's just opening faster and that much easier to use. So there are 2 programs that I use for getting these files ready to be reverse engineered, and those are Meshmixer and Meshlab. Now, Meshmixer is an AutoCAD product. Shh, don't tell anyone. Both these programs are free. Meshmixer is very user-friendly. It gives you a paintbrush. You can adjust specific areas of model and basically paint over them to fix them. It's kind of if you're familiar with Blender, it's mainly used for that kind of workflow, but I kind of make it work for what we need. And then on top of that, we also have Meshlab, which is a phenomenal program, super powerful, and extremely user-unfriendly. It is probably the worst program I've ever used as far as user friendliness goes. When I first started talking about this, I likened it to taking your Ferrari to go get groceries, and I think a better analogy would be like taking the space shuttle to go get groceries. It's designed for something so much higher than what we're using for. It's not really practical except for this very specific use. So let's take a look at what that particular workflow might look like. So if I open up Meshmixer to start off with. So this is the Meshmixer interface, and in order to work with a scan, we want to import that geometry into Meshmixer. So we're going to click OK, hit import. We're going to import our part. We go through it, and it generates the mesh, and just like that, we have our 3D geometry. As you see, that is much faster than SOLIDWORKS could ever hope to open up a model like this. Now, in order to be clear on what we're doing, I'm going to turn on View, Show Wireframe, and now we can actually see the geometry that we're working with. And actually, that is not the model that I wanted to open, so I'm going to replace that. That was one that I reverse engineered. And we're going to go with the raw scan data. So this is actually what you get from the scan data. And this one, it's not the prettiest. I did have some flaws in here. I didn't bother fixing them because it's kind of not relevant for what we're using. But in the bottom right corner, I don't know if you can see, but this particular model coming from the Creality scanner has 338,000 faces. So again, this is the model that took 8 minutes for SOLIDWORKS to open. And we're going to reduce the number of faces that are on this model to make it easier for SOLIDWORKS. So the tool we're going to use is what's called the Sculpt tool. So if you click on that and then go to brushes, you have a whole bunch of different options that are here. Like I said, this program is designed for 3D sculpting and basically clay modeling virtually. But what we're going to use it for is down at the bottom, you can either refine, which will add additional triangles to your model if for some reason you want that. We're going to be reducing or using adaptive reduce. For this use case, they're both the same. So we're going to click reduce. And now you see we have our paintbrush preview. So I'm going to click here. I guess on the left we have our sliders, so we can adjust the strength of the reducing, the size of our brush, and then depth if we want it to reduce both sides apart. Probably won't want that. So I'm just going to click a big flat area here because flat areas are easily reproduced by triangles. So I'm going to reduce the number of triangles that are there. So if I click and kind of paint on this area, we can see that it is quickly reducing the number of triangles there. If I want to make this faster, I can click on size to make it a bigger brush, click and paint, and just go through and paint all of the flat areas that we really don't need a level of detail on to reverse engineer because they're all just flat surfaces. Now, if you watch the bottom of this model as I go over it, the bottom does change. So that's something to be careful of when using Meshmixer. If you need the geometry on the bottom to be identical to what you have, you may need to reduce your brush size or find another workflow that's maybe a little bit more fluid for that. So I'm just going to, again, paint the flat areas, hit this back area, and then the biggest reduction is going to be on the bottom, which is huge and flat. And I'm just going to get really ugly here, paint that whole area. So what we have here is essentially the same model that we had before, just with greatly reduced fidelity on the flat areas that we're not really concerned about. And in doing so, we dropped it from 330,000 triangles to 300,000. Not a huge reduction, but definitely enough to make a difference. And again, we're not adjusting the accuracy of the model as well. So once we have it happy with where we have it, we're going to go to export. Click export. That'll give us a option, and I'm going to save this as prismatic demo reduced, if I could spell. So there we have the rough boundary work done in Meshmixer. Again, this is just designed to reduce specific areas, and we'll do the heavy lifting in Meshlab. So I'm going to close out Meshmixer. Don't save it. And I'm going to open up Meshlab. So again, this is a very powerful program. It is designed specifically around mesh engineering, as you might imagine by the name. But from what I've found online and people using this, the main market for Meshlab is people doing full skeletal scans or dental scans, so very high accuracy. You cannot lose the fidelity of your scans even if you reduce the scan triangle count. So it's very good at that. So I'm going to go ahead and open up the scan that we just finished. Reverse engineering, demo reduced. And we see it opens up even faster than Meshmixer did, and we can spin this around. Now if we want to be able to view the triangles like we did in Meshmixer, again, this is an extremely unuser-friendly program, but if you look up at the top here next to the project, it has the project name, and then right here, there's a little black box that has lines through it, and that is turn on the wireframe. So you click on that, and now we can see what it actually brought in. And you probably can't see the data on the bottom, but down here it says this particular model has 300,340 faces with 150,000 vertices. So we're going to go ahead and take that down into something that's usable by SOLIDWORKS. And if you learn nothing else about Meshlab in this lesson, what you're looking for is under filters, remeshing, simplification, and reconstruction. And so you get this huge list that I have no clue what any of it does, full disclosure. But we're only concerned with simplification, quadratic edge, collapse, decimation. So we click on that, it gives us a target. So it offers a 50% reduction, so 150,000 faces from where we are now. And I'm just going to click apply. And when I do that, I want you to pay attention to the model itself and see if you can see any change in the shape or anything that goes along with that. So if I click apply, just that quick, the model itself stays the same, except you get a reduced number of triangles. If you want to go through that again, you can go to filters, remeshing, simplification, reconstruction, quadratic edge, collapse, decimation, half of where we are now, 75,000 triangles. That seems reasonable, so I'm going to hit apply. And again, watch the model. Nothing changes as far as the geometry goes, but again, it's that much lighter for SOLIDWORKS. Now, as you're making these changes, before you hit apply, you have to be sure that your settings are right, because as I said, this is a very unuser-friendly program. There is no back button. So if you screw up, you have to close everything out, reopen it again, and then do what you did. So it's brutal in that aspect, but again, for what it does, it is extremely powerful. So once we have our mesh reduced down to something that's probably digestible for SOLIDWORKS, we're going to click File, Export Mesh As, and give this a name, save it, click OK. And if you're able to read the part down here on the bottom right, it does tell us that the file was saved properly and it was saved in 111 milliseconds. So now all that fun stuff is done, prep work's done, we can bring it into SOLIDWORKS and actually get to engineering. So if we go into SOLIDWORKS, we can open up that file we just saved. If I can remember what I called it, Meshlab, there we go. So it does tell us, give us a warning, there's 75,000 facets, which I'm not really concerned about that because I know that I took it into Meshlab, Meshmixer, did the prep work, got all that fun stuff done on the back end. So now it's should be opening it relatively quickly. And of course, it always seems that much longer when you're giving a presentation.
Is there a reason to not go straight to Meshlab to begin with?
So if you have specific parts of your scan that aren't relevant, for instance, this helmet will be later, I'm only concerned about this top part, so I could reduce everything else down below in those specific areas and then take it in Meshlab, and it does everything else proportionally. So it's a great question. All right, so now if we're going to reverse engineer this, from here, if you're familiar with SOLIDWORKS, the workflow is probably pretty familiar. Now I didn't reorient this or anything, so I don't know where it is relative to any planes. But what I would do for this particular model is these edges that are kind of curved and filleted and stuff, those are actually just horribly scanned data. These come to a sharp edge. So I'm going to come to the bottom, click on one of these faces, doesn't matter which one I do, and create a sketch. So now I'm sketching on this bottom face, and I want to basically reproduce the outline of this part to match our scan data. So what I'm going to do is click outside of the model. And in doing that and drawing my sketch larger than what it needs to be, I know that none of these entities that are in there right now are snapped to anything in my model. You know, if you click on the model, it may click to one of these vertices or whatever. I don't want that. So I just drew a simple rectangle, and now I can take, for instance, this line and tell it that line is in the same plane as this vertex. So I click the line, hold the shift key, click the vertex, and now I can tell them those lines are coincident. Same thing with this top part. Tell them those are coincident. And same thing with the bottom. And I promise it's going to get more exciting than this, but we're just laying the groundwork for what we're doing later. Wow. There we go. So I would go through and actually remodel the bottom of this, give it the curved part, and then when it comes to actually extruding this, we can use, well, if we had a set of calipers, we could take a height measurement on it, but in this instance, what I would do is feature extruded boss, and I'm going to use the 3D scan geometry again to define what we're extruding. So I'm just going to give it a up to vertex, click on this face, and have it go up. And because it is having to, important thing, if your scan was brought in as a solid, you cannot click merge result because we're using the geometry from the scan as a reference in the sketch itself, so we get some zero thickness geometry. So if you uncheck merge results, click OK, it should give us so that'll be the base of our scan. And I would go through and work on the rest of this, put in my curve and everything and run with that. So any questions so far on that general process before we go into something a little bit more interesting than just drawing a simple block?
Is there a benefit to saving it as OBJ as opposed to other file formats?
That is a great question. For the purpose of this, OBJ, step files, all that fun stuff, they're pretty much interchangeable. When it comes to saving out in other formats, given the choice, I generally save as a 3MF. If you're not familiar with 3D printing and 3MF files, that's something that's been developed specifically for 3D printing. So I try to defer that in most cases, but for reverse engineering, it's whatever format you prefer. Good question. All right. So now that we've done our reverse engineering, we're going to go over what's probably a little bit more relevant to what most of you are looking for, and that is organic shapes. But before we do that, we're going to go into a little bit of storytelling. So, as I said before, I'm from Wisconsin. It gets cold, it gets snowy, it gets miserable, and during the winter, there's 3 things we like to do. And those are drink beer, eat cheese curds, and play hockey. And a surprising percentage of time, we actually do all 3 at the same time. So, I picked up hockey as an adult, and I don't know if I was a glutton for punishment from the start or if my mom dropped me as a kid or whatever the case may be, but I am a goalie. So, when I play the position, the whole point is to get in front of the puck and stop it. And when I first started, I was horrible. I was always out of position. The only thing that would save me was the little bit of athleticism I have. I could generally stop it, but I had no clue on where I was relative to the goal behind me. So as an engineer, I thought about the situation, and I came up with a solution that I'm going to videotape my goals, or my games, and then I'm going to watch and see where I was and figure it out from there. So I started doing that, and I got better and better and better, and eventually I figured out that I was not the only narcissist on my team. My teammates liked watching each other too. So I put the videos up on YouTube, and then they would watch it, and they would share it with their friends, and occasionally I would have random people on YouTube find my videos, and before long, I would post a video and there'd be literally tens of people that would watch them. Sometimes it would go viral and I would get a couple hundred views, and that, man, I was feeling that. Now, when you have that level of internet celebrity, the pressure that's on you to come up with new ideas is immense. So I started thinking about what can I do to spice up the videos? And the solution I came up with was, I have a scanner, I have a goalie helmet, I have a GoPro. what if I could just put a GoPro on the helmet? So they make standard stick-on mounts and stuff, but when you have a hammer or a scanner, everything looks like a nail. So I took that prototype scanner I had, and I took a scan of my helmet here. And that's what we're gonna be working with for the rest of this session. So if we kind of look at what we did with our workflow prior, it's gonna kind of follow along the same path. So first step was I brought it into Meshmixer, and I reduced the areas that I didn't want, and I'm gonna actually close this out. I'm gonna reopen Meshlab. So I took the scan. Now this scan was, I wanna say it was something insane like 12 million triangles. SOLIDWORKS couldn't even fathom opening up that particular file. So I took it into Meshlab, reduced some areas, used their clipping tool to take away a lot of the stuff that I didn't need, and then I brought it into Meshlab. So if I show you what that looked like when it first started. Okay. So this is what I started with when I actually brought it into Meshlab. So again, this is the only relevant part that I had. You see this kind of orange or pink part. That was tossed in by the Riven software to fill in that gap. But again, I know you can't see the bottom here, but just this little chunk of the scan is 1.4 million faces and about 700,000 vertices. So immense file, and this is not a solid file. This is simply a surface. So there's no thickness to it. And there's no chance you do anything with that in SOLIDWORKS. So again, taking it out of here, I would go into Filters, Remeshing, Simplification, Reconstruction, and Simplification, Quadratic Edge, Collapse Decimation. You guys kind of getting the workflow here? So I click on that. Half of that value is 673,000. I'm going to knock that out of the water, and I'm going to go down to 30,000 faces. And again, when I hit Apply, it very quickly will take that scan data, figure out all its funny stuff on the back end, and give me a 75% reduction in triangles, or way more than that, 95% reduction in triangle, just like that. So again, we can see this is now a much more faceted design, but it's still at 30,000 faces, still relatively smooth. I can definitely work with that, especially for what we're doing here. Now, on something that's symmetrical, you can, of course, slice this in half and work on half of this, but in this case, this helmet is hand-laid fiberglass. It's not perfect. It made sense to scan the full section of the helmet that I was working with. So once again, once we have everything where we need it, we're gonna go to File, Export Mesh As, and in this case, I've done this presentation a time or two, so we're gonna find some way to name that uniquely. Click OK. And just like that, it has exported it in 4 milliseconds. Way faster, definitely worth the time to get it done before you break it into SOLIDWORKS. So now that we have it exported, we can take it into SOLIDWORKS and start working with it. Now, little peek behind the curtain, that's the eventual goal we're going towards, but we're going to open up the model as it is right now. Mesh demo, there we go. Click OK, and now it's going to parse the file. We see that at 30,000, it didn't even give me a warning telling me that there's a lot of facets in this model. Even SOLIDWORKS doesn't freak out about opening something that small. And we end up with a very usable SOLIDWORKS reference. Now, there are some tools that you may be able to use at this point. SOLIDWORKS has their Scan to 3D tool, which they put a lot of work into. It's a phenomenal tool for prismatic solutions and other things. Some of this works organic. It doesn't work the greatest. It kind of parses it into some kind of shaped blobs that I think we can do better. But for an automated tool, it's definitely not bad. So now that we have a usable scan that we brought into SOLIDWORKS, we need to figure out exactly what we're going to do with it. And this is where it kind of slices off into from a scanning conversation into a surfacing conversation. Now, if you're not familiar with surfacing in SOLIDWORKS, there are a lot of nuances to it. It's something you definitely need to practice to get usable, to get pretty good at it. But I can kind of walk you through how I did this model, and hopefully that takes some of the scariness out of surfacing. So the big thing with surfacing is you need to find a way to define what we're looking for. In this case, I'm just looking at this part to this part of the helmet, and I already have that cut up. So I want to create a line on the front portion of the helmet and a line on the back, and then we're going to say, here's the starting endpoints, kind of merge in between that. So the easiest way that I found to do that is to go into Sketch, and since we don't have a plane that easily divides this part, because we didn't manipulate it at all when we did the preparation, we're just going to work with it as is, and we're going to give it a spline. So again, if you're not familiar with splines, I guess I did not start a 3D sketch, 3D sketch, and then splines. Now, splines are great for working like this that aren't perfect geometry. They really do a good job of capturing the smoothness and the organic nature of a model like this. So we already have our scanned data in here, so we can kind of use these triangle vertices to define what our spline is going to be. So if we zoom in real quick, we can start clicking on vertices and start reverse engineering what this shape looks like. So I promise I'm not going to make you sit through me doing this entire model like this, but I at least want to get started. And when I'm doing a spline in a 3D sketch, in this case where I have some parts that are relatively flat, I have these ribs that are kind of swoopy, I try to do at least one spline on the flat edges and one spline at each inflection point as the geometry changes. So as it goes from flat up to curved, I'll want to put a point there, and then it goes up this curve and I'll put another one there, and so on and so forth, and kind of work through there. And I'm not going to bore you with the entire process, but that's how it goes. The important thing is, when I was clicking those individual points, I was making sure that the orange ball highlighted first, which tells me it's going to lock that point to the scan data. It's very easy to come through here with a spline, and if you're not paying attention, you click here instead of on the orange ball, and now okay, that one actually worked surprisingly well. But usually you'll have a spot that flies off into nowhere. If that happens to happen, you can click on that individual point, hold Control, click on the vertex, and then make them coincident, and now it'll lock the point to the triangles themselves. So, little handy use case for that. Now, there is one workflow that greatly simplifies that, and my coworker Matt figured this out last week, which I really wish he would have figured this out 2 years ago when I was actually starting this stuff. But one of the improvements that SOLIDWORKS has made is they actually, with their manipulation of mesh geometry, you can now do an intersection curve or a lot of other operations that you couldn't do prior. So in this case, what I want to do is I'm going to work on the front edge here, and I'm going to create a plane that intersects generally where I want it to go. So if we kind of mouse over our planes, we see the front plane is way off in the distance. Top is close, but it's at an angle, so there's nothing that's easily workable, so we're going to create our own geometry here. So I'm going to click a feature reference geometry. I'm going to get out of the sketch first. Go feature reference geometry, and I'm going to insert a plane. Now, there's a number of different ways you can define planes, but in this case, the one that probably makes most sense is if we choose 3 points on this scan that are generally in the line that we want it to do, it'll put in a plane for us. So if I go one there, and I try and pick them apart as far apart as possible to get the minimum number of deviation, or minimum amount of deviation. But those 3 points, or 2 points, I guess. The third point, come on, there we go. So that gives us our plane that we're going to be working from. And now we can go, without having a sketch open, we can go to the Sketch tab, and under Convert Entities, and click that down and go to Intersection Curve. So now it asks us for what entities we're looking for. So I want to give me a line where this plane is intersected by this mesh. And you have to click into your bodies folder and click on the mesh there. We'll click OK. And hopefully this won't take too long, but generally what it's doing is it's calculating all the different places that that mesh intersects the plane. So it's going to give us a much more accurate definition than what I did before by hand drawing splines, but it's also going to be a much more resource intensive process. So we see where prior I had, maybe 10 points that I put in, this line has 2 points or 1 point for every time it crosses a single line. So huge amounts of data there, and that's a pretty good starting point for our splines. Now the surface is curved, so if I were to simply tell it to loft between these two curves, it would just give me a straight line and it wouldn't represent the actual shape of the helmet. So the way I would get around that is if I click on the plane, hold the Control key to copy it, maybe not. This was working earlier. Oh, thank you. So yeah, I am still in that sketch, and it's now flipped out. There we go. Okay. So now if I try and move this, try and make a copy of this plane, it hopefully will let me. There we go. So by holding the Control key, clicking on the plane and moving it, I can create a new plane, and I would go through that same intersection curve process however many times I think is relevant to give me a pretty good approximation of the shape of that helmet. So when you go through that, I'm not going to go through it now, what you'll probably end up with, or what you should end up with, is something like this. So if I show that surface body, we can see there's our original scan data, and then we have a series of intersection curves along here, and we also have the one that I drew on the back edge that comes up with that. Now, one caveat to this particular process is it gives us a data point for every single time that plane crosses one of these lines. And this is an immense amount of data. When I tried just simply lofting from this front point to this back point, it took, I want to say, roughly 10 minutes just to give me that initial surface. So it's not really a usable process at that point. And the key to that is I'm going to hide my scan, just make things a little bit more clear. Once I have these intersection lines in place, I'm going to go back into my sketch, and I'm going to highlight a series of them, one set of them, and I'm going to go under Tools, Spline Tools, and Fit Spline. Now, if you're not familiar with Fit Splines, they are a phenomenally powerful tool in SOLIDWORKS. You can use them in a lot of areas where you don't have exact geometry. For instance, if you're making a surface and you have a straight line and then a curve, if you're trying to make a surface out of that, it can be kind of pain because you either try to model the straight line or the curve, but not really both. If you turn that into a split line, it understands it's one line and it works together beautifully. So I'm going to click Fit Spline, and now we zoom in and see that it takes all these little line segments and puts them into one smooth curve. Sometimes it'll give you a really rounded bottom here, and that's because this check marks for closed spline is turned on, so it tries to make a circle. Make sure that's turned off, and then for our purposes, I'm going to turn on delete geometry. So what that's going to do is that's going to take all the little individual points that are making up this line right now and delete those out and just give me the spline that fills its place. In this case, it's going to make sure that every point on that line is within 0.006 millimeters, which is certainly close enough for anything that we're going to be using it for. And we see, instead of having all these little minute line segments, we now have one smooth curve that can be used. So again, just like before, I would highlight the next one, go into Tools, Spline Tools, Fit Spline, making sure delete geometry is turned on, close spline is off, and just like that I have another set. Any questions on that? All right, I guess no one's moving around enough. All right, so I'm going to do this one last time to get us to the next step. So I'm going to Tools, Spline Tools, Fit Spline. Thank you. Okay. All right, so we now have our lines running longitudinally that we're going to use to reverse engineer this shape. And what I'm going to do now is make lines that run front to back to connect all those points. So I'm going to start a separate 3D sketch. Now this can be done in the same 3D sketch, but I like putting them separate so I understand and can hide one versus the other. So I'm going to turn on another 3D sketch, and again I'm going to go to my spline tool, and now I'm going to click this line to this line to this line to this line. Hit escape to get out of that command, hit enter to re-enter it. Okay, it's not going to. And then do the same thing going all the way across this part. Now, when I try and figure out how many of these lines that go along, I like to use the same rule of thumb that I did when I was drawing in that first line initially. I like to put at least one on flat areas, one at each inflection point, and that's generally a pretty good rule of thumb. So you can see how that would work as it goes along this, this 3D sketch. I'm not going to bore you with doing that over and over and over again, but eventually what you'll end up with is something like that. So at this point we can definitely see the shape of our helmet starting to take shape, and now we can actually start with the surfacing of it. So under our surface tab, so we click on surfaces, and the best tool I've found for this is going to be a boundary surface. Now you could do a lofted surface between here and here. A boundary surface gives you a lot of the same options as a lofted surface. It's just less specific about start and end points. So in this case, we're just kind of eyeballing a lot of this, using this direction 2 versus a lofted guide curve is going to be a little better solution. So I'm going to choose the front line for one of our sketches, and because these lines are not connected, and because I did them in 2 separate sketches, I now have the ability to choose just that line, and when I do that, it gives me the selection manager pops up. So in this case, I'm going to choose an open loop, click the green check mark, and now it understands that's going to be one of our lines for the starting loft. I can do the same thing for the front part, so if I click on that line, again it gives me the selection manager, so it understands that this is a partial loop, hit OK, and now it gives us our 2 loops. Now, in this case, it had 2 different ways to put these connection points. So anytime it has a 50-50 choice, it's going to choose the wrong one 90% of the time. It's simple statistics. So if this happens, it's simply right-click on one of them, go to Flip Connectors, and boom, we have our surface. Now, it looks pretty good to start off with, but if we look in closely, we see it doesn't quite follow some of the geometry we had. And again, this is what I was talking about, where it simply takes a point on this line, a point on this line, and connects them straight, which isn't really representative of what we're working with. At this point, I like to turn off Show Preview, only because as it's chugging through each of these individual guidelines we're going to give it, it really slows down trying to give you a graphic representation. So now we can click into our direction 2, which is going to be these longitudinal connection lines we have. So I can go through and click on this line, tell it OK. And we see that even though it's not giving us a preview, it is taking a substantial amount of time to calculate, because it's still doing all the computations on the back end, but it's trying to figure out what this curve looks like as we add these additional guide curves in. And I promise you, I'm not going to make you sit through all of this, but I do want to get in a couple just so I can show you the effect that these guidelines have on the overall shape relative to our model. So I think one more should give us a pretty good representation of what that section of the scan would look like. So I now have 5 guide curves in place. I can hit OK, and that's going to alter our model. Now up here we see that it's having the guide curves on this side versus over here. It doesn't quite know what's going on in this middle area, so they get a little weird, but I'm going to focus primarily on this area that we put these guide curves in, and I can add zebra curves to give us a representation of what that flow looks like as the reflections model off it. And it looks pretty smooth. I'm just looking for a nice smooth transition from here. No steep creases or anything like that that would indicate that maybe one of those points wasn't connected directly to the scan data. And if I want to kind of get another visual confirmation, I can turn on our initial scan data, and we see that over on the right-hand side, or left-hand side, excuse me, it's nowhere close, but over here, there's sections that are a little high on our model, sections that are a little low, but that looks very close to what we're actually going for. So any questions on building the surfaces using the sketches that we laid in place? All right. I'm either doing a really good job or no one's paying attention. So all right. So once we've done that enough, eventually what we're going to end up with is this curve here. So that is a pretty good representation of our scan data. Again, we can turn that on, show, and we see that's a pretty good match. The curvature seems to be generally in the right place. The only thing left is we have a couple hole cutouts, and this is going to be our last kind of quick section on modeling using the scan data. So if I want to cut out the patches that are in place, what I found probably the easiest way to do it is if I press the tab key to hide the scan or hide our surface. That takes us back to our scan data, and now we're going to do a sketch that represents our hole cutouts. So in this case, I'm going to do a simple two-dimensional sketch. So sketch, sketch, and choose a plane that seems somewhat close enough. So top plane allows me at least to see the areas that I'm concerned with, but they are kind of distorted, but we're not worried about that because it'll all work out in the end. So just like before, I'm going to do a spline. Click on some edges here that represent our points. Now you do have to be careful when using the edge of a scan, because as the scan is going along, it's taking measurements off of all of the geometries there. But as it gets to the edge of the model, it gets no return. So you can end up with kind of a jagged edge. You could end up with some pretty nasty, not necessarily good data along the very edge. So you have to be careful of that. But in this case, I know that one, the scan data turned out okay, and two, I'm not needing something super precise here. So I simply go through, create a spline that fits that hole. And again, not super concerned about the accuracy here, but there's another one. And if we spin, we see that it's not really orthogonal to our model itself, but if we bring back our surface, so if we click on that and go to view, even though it's not cutting directly, we can go into our surfaces. We're going to get out of our sketch, and now we're going to use trim surface. So right now our sketch is highlighted. If I happen to not have it highlighted and go to trim surface, it simply asks for a trim tool. So we have our sketch that is already defined, and then you can either have it keep the intersecting areas or remove the intersecting areas. So we're going to have it remove, maybe. So you could do a projection onto the surfaces, but in this case you don't have to, because it's going to basically take a 3D projection of that off of the sketch plane that we were in. So that's kind of what I was talking about with, it doesn't really matter if your plane is orthogonal to your scan itself, as long as it's able to see the entirety of the cutout, you don't need to worry about that. But it is flipping out, and I think what it's trying to do is also cut my scan, which is going to be horrific and slow. So before you do that, you want to make sure to hide your scan data, or else you could end up in a very long, drawn-out process. So from there, once you have the surface done, you simply give it a thickness, in this case is 3.5 millimeters, give or take. And what you end up with is a completely usable 3D scan data in SOLIDWORKS that you can then reverse engineer a GoPro camera mount in this case. So the ultimate question is, did it work? So, come on.
How long did it take to break the camera?
So that was an important part of the design process, is I tried to put it as far back and down as possible, and that's why I didn't want to use an off-the-shelf mount. Fortunately, when I have it on, from the puck's point of view, it's relatively guarded, so I have not had anyone hit one yet. I mean, Lord knows they've tried, but no one's been successful. So,
You just made a target.
yeah, exactly. But you know what? If it hits my helmet, it doesn't go in the net. So, yeah, it's probably more of a instance of maybe I'm not playing with the highest skill players. Again, I am relatively new, but this is what the end result looks like. So now you can shame all of your teammates and opponents and tell them how slow they're going and they couldn't actually score if they wanted to. So. And that is my process for bringing scan data into SOLIDWORKS and reverse engineering from there. Are there any questions?
How big of scans have you worked with in Meshmixer and Meshlab?
Sure. So this helmet scan was probably the biggest one I did. Like I said, it had over 10 million triangles, I want to say, so it is immense. As I said, the use cases I found for Meshlab on people putting YouTube videos, most of them seem to be either dental scans or forensic scientists that are doing like entire skeletal remains. So from this simple necessity of how big those files have to be, I've not found a limit for it. I'm sure a lot of that's going to be hardware dependent, but I've not found that limit yet.
You might have scans in like 15 gigabyte to like 200 gigabyte range.
So you should email me and let me know if you find the limit. And that's kind of the crazy part about this is, 10 years ago, this workflow would have been very, very practical, but nowadays where there's so much scan data out there, there's from the 3DX platforms, people are scanning entire factories and reverse engineering it in there, and something like that would kill SOLIDWORKS in an instant. So if you're getting to that level, maybe even this workflow is not the best, but there may be other tools out there that are a better fit. Great question. Anything else? All right, well, they said end it 5 minutes early, so we are right on time. I'll go ahead and turn you guys loose for your next presentation. Thank you very much for your time. Feel free to reach out if you have any questions.